All right, an example of finding the centroid by integration. For this, I picked this shape. It's really this shape right here. I drew it up in Excel, so this is part of this function that's continuing over. And this function is y is equal to x to the fourth. And so I have it starting at 0, 0, and at x is equal to 1. If you put 1 to the fourth in there, you'd get 1. So this is just that function. We're actually only finding it between 0.6 and 1, though, if you notice. This blue shape is what I want to find the centroid of. And we're going to, these are like in meters. So if you had a shape that, maybe you had this cut on a CNC machine or something, and this is a piece of aluminum. I mean, you could have this shape here and know that this side is bounded by that function, and then you could calculate this centroid. So do we want to do a horizontal element or a vertical element? Well, let's go back and look at this a little bit more clearly over here. We have this area down here that gets kind of caught by the limit of integration. So this shape down here is quite different from the shape up here. So when we look at it here, if I went to use a horizontal element, and I'm not saying I want to do this. Matter of fact, I'm going to go on the record and say I don't want to do this. I mean, we could do it, but we're not going to do it. We're going to do the vertical. But let's at least talk about why the horizontal is maybe problematic. If we have a horizontal element here, this is what I was talking about on an earlier slide. This differential element is actually going to be equal to the, its width is equal to the upper bound of integration, which is 1 minus x, because this whole length right here is x, right? I mean, if you plug in the x for the function, here you plug in this x, you get that y, right? So this width here is 1 minus x. And so the centroid there is going to be equal to the average of this x location and 1. So x plus 1 over 2, and that will give you this. There's other ways that you could write that, but that's basically what it boils down to. Down here, for this particular problem, I mean, think about it. This thing is 0.4 wide. Okay, its distance here is x, and so the location of the centroid would be x tilde would be equal to x plus 0.2. This is actually kind of a simple little element down here, but it does complicate things, because then you're going to have to break this up into little composite areas and whatnot. This isn't really the way I would solve this problem. Instead, I would look at it this way with a vertical element. The vertical element starts at 0, goes up to the height of y. Y happens to be equal to x to the fourth, by the way. Its width is going to be dx, which I don't have drawn here. Shame on me. And the centroid x dimension is actually x tilde is equal to x, because it's just a differential width. It's tiny width. Its centroid is actually going to be right there on the at the value of x for the equation. And the height of the centroid is half of the y value. Since this is a rectangle, the centroid's at the half height. So y tilde, which is the centroid of the differential area, is going to be equal to y over 2. So you have to get your tilde, like your y tilde and your y. Make sure that you've got them differentiated. And here you can see x tilde is equal to x, but if we had used that other horizontal element, it would have been different. So you just have to draw all this out. Surprise, surprise, that I've told you to diagram something. And so if we're doing a vertical element, we have dx here. We know that our function needs to be written in terms of x, right? Which is great, because we actually already have it written in terms of x. So what is dA equal to? Because we need to integrate dA. Remember I said we needed to break it up into its component parts. Where it's going to dA is the area of this element. It's going to be equal to y, which is the height, times dx, which is the width, the area of a rectangle, right? That's y dx. And y happens to be equal to x to the fourth. So dA is equal to x to the fourth dx. So now we've got an integral that is in terms of dx, so we can integrate with respect to x. So integrate with respect to x, and being a definite integral, we need to put our upper and lower bounds as the bounds from the x-axis. Okay, if we were doing the horizontal element, then we would have had a dy as our height, and we would have needed to find the element, the limits of integration for the y-axis, which would have been like 1 and then down to whatever this value is right here. How would you find that value? Well, we know 0.6. You do 0.6 to the fourth. That would give you the y value right there. That would be our limit of integration if we had been doing a horizontal. Now you can see why I didn't want to do the horizontal. I want to do the vertical because now my limits of integration for a vertical element are going to be my x values. It's going to be 1 is the upper limit, 0.6 is the lower. All right, so bear with me. We got some calculus. It's not much. It really isn't. We have x bar is equal to the definite integral from the lower limit to the upper limit of x tilde dA over that the integral from 0.6 to 1 of dA. Remember that denominator is just going to be the area under the curve. It's the area of the blue. All right, but up here. So I've got x dA, and don't forget that dA is equal to y dx is equal to x to the fourth dx. So up here I have x tilde is equal to x, and then I have y is equal to x to the fourth dx. So that's why I have x times x to the fourth dx. And then underneath, this integral is just y dx, so it's just x to the fourth dx. So doing that math, that's not too hard, right? X times x to the fourth, that's x to the fifth. And so then integrated, I get x to the sixth over 6, and x to the fourth integrates to x to the fifth over 5, and then evaluate that at the values of the definite integral, and I get 0.1589 in the numerator and 0.1844 in the denominator. That number right there is going to be useful to keep because we're going to use that in the next integral. And if you're doing a bunch of symbolic work here, you know, sometimes if you're finding both, I would not be simplifying, you know, canceling out between above and below if you can pull out, you know, constants and things like that. You know, like if there was a 1/2 in there or something, I wouldn't pull that out and start working with the numerator and the denominator. I'd keep them separate so that I get this number, which actually is the area. And then you can use that exact same one in your other equation, in your y bar equation. But anyway, so I've got 0.1589 divided by 0.1844. That gives me 0.862 meters. That's the location of the centroid, 0.862. You know, it's like somewhere over there-ish, right? And, you know, left to right, that's probably about where I'd put my finger to balance this if it were a plate of constant thickness, right? So that's, you know, you get a good gut instinct at 0.862. I think looks pretty good. So doing the same thing for the y, here we know that the dA is equal to y dx, which is equal to x to the fourth dx. That's the same as before. And recall that y tilde, this is where we have a little bit of difference. I'm integrating y tilde dA, so y tilde is equal to y over 2. Okay, here's where I'm saying like you might get a constant that you might want to factor out and things, and just be, you know, like here it factors out. I wouldn't have combined it with this number if this were the first one I was doing, because then it would have muddied up that bottom number, and I would have liked to keep it separate. But anyway, so y tilde is equal to y over 2, which is equal to x to the fourth over 2. So that's that height right there, the height to the centroid of the differential area. All right, so do the same thing. Except for now, y bar is equal to the integral of y tilde dA. The only difference is instead of an x tilde, here we have y tilde. So y tilde is equal to y over 2. So now we have y over 2 times y dx over this. Look at this, the bottom. Remember, we calculated it already, so we have it here. If you were doing this from the beginning, remember, we would have had to have done this integral, but it was already been done. All right, so y over 2 times y is y squared over 2. Better yet, y is equal to x to the fourth, right? So I can go in here, I'm factoring out my 1/2, and then I've got 1/2 the integral of y squared dx, so that's x to the fourth times x to the fourth, which is x to the 8th dx. And then down below, like I said, I've already got that integral done, so then I just do my integral here, and I get x to the 9th over 9, again, plugging in my limits of integration, evaluating, and you get 0.298 meters, which is, you know, maybe like right there-ish. And that seems like a really good place to put your finger to balance it. So, you know, I think that number seems pretty good. You got to use your calculus for something real. How cool is that? All right, here's our results. We have 0.862 and 0.298, just the values from the last slide. And there's that centroid. And So since we're doing this using calculus, our origin down here at 0, 0 is where everything's going to be from that origin. So it's 0.862 in the x, 0.298 up, and there you go. That's your centroid.